Welcome. In this video, we will explore the fundamental concepts of reasoning and proof, which are central to the IB mathematics analysis and approaches higher-level curriculum. By the end of this session, you will be able to understand the purpose of mathematical proof, use logical connectives to build arguments, and apply two key proof techniques, proof by deduction and proof by equivalence. Let's begin by considering what a proof is and why it's so important in mathematics. Unlike science, which relies on experimental evidence, mathematics relies on logic and reasoning. A mathematical proof is a correct argument that establishes the truth of a mathematical statement. A proof is a correct argument that establishes the truth of a mathematical statement. Every proof follows a logical structure. It starts with assumptions, called hypotheses, and through a sequence of correct mathematical steps, it arrives at a conclusion. So a proof begins with hypotheses, proceeds through a sequence of correct steps, and ends with a conclusion. The purpose of proof is multifaceted. It helps us to be convinced that a statement is true, to understand why it is true, to communicate mathematical ideas, and even to discover new mathematics. Proof serves to convince, to help us understand, to communicate, and to organize our thoughts. Let's look at a classic example to illustrate the difference between a conjecture and a proven statement. Consider the conjecture. If a and b are real numbers and a is less than b, then a squared is less than b squared. We can test this with a few examples. If a equals 1 and b equals 2, then 1 is less than 2, and 1 squared is 1, which is less than 2 squared, which is 4. This example supports the conjecture. Let's try a equals 1 and b equals 2. 1 is less than 2, and 1 squared is less than 2 squared. This works. However, a single counterexample is enough to disprove a conjecture. Let's try a equals negative 2 and b equals 1. Here, negative 2 is less than 1, but negative 2 squared is 4, and 1 squared is 1. 4 is not less than 1. This is a counterexample. Because we found a counterexample, the original conjecture is false. This shows that examples can help us form conjectures, but they can never prove them. Only a rigorous proof can establish the truth of a statement. To build proofs, we need a precise language. This is where logical connectives come in. They allow us to combine and modify mathematical statements. We will now discuss logical connectives. Let's look at the most common ones. The connective AND is called conjunction and is symbolized by an upside-down V. The connective OR is called disjunction and is symbolized by a V. Not is negation, symbolized by a tilde. If then is implication, symbolized by a right arrow. And if and only if is equivalence, symbolized by a double-headed arrow. Let's focus on two of the most important connectives for proof: negation and implication. First, negation. The negation of a statement A, written as not A, is its opposite. If A is true, not A is false, and vice versa. For example, if statement A is x is an even integer, its negation, not A, is x is not an even integer. This is a crucial concept for proof by contradiction, which we will cover later. Next, implication. An implication, written as A implies B, means that if statement A is true, then statement B must also be true. In the statement A implies B, A is called the hypothesis, and B is called the conclusion. We can also say A is a sufficient condition for B, or B is a necessary condition for A. A common mistake is to confuse an implication with its converse. The converse of A implies B is B implies A. The converse of A implies B is B implies A. It is vital to understand that a true implication does not guarantee a true converse. For example, consider the statement, if x equals 2, then x squared equals 4. This statement is true. If x is 2, then x squared is indeed 4. Now let's look at its converse. If x squared equals 4, then x equals 2. This converse is false. While x could be 2, x could also be negative 2. So the conclusion does not necessarily follow from the hypothesis. This distinction is fundamental. A proof must establish the truth of the statement as given, not its converse. Now let's discuss our first major proof technique, proof by deduction. This is also known as a direct proof. Proof by deduction, or direct proof, is a method where we start with the given information, the hypothesis, and work forward step by step to reach the conclusion. Each step in a deductive proof must be a correct implication. We are essentially building a chain of if, then statements. The structure is A implies B, B implies C, and so on until we reach our conclusion Z. Let's work through an example. We will prove a statement about consecutive integers. Our goal is to prove that the sum of any three consecutive integers is divisible by 3. First, we need to represent three consecutive integers algebraically. Let's call the first integer n. So our three consecutive integers are n, n plus 1, and n plus 2. Next, we need to find their sum. We add them together. The sum is n plus 1 plus n plus 2. Now we simplify this expression by collecting like terms. N plus n is 3n. 1 plus 2 is 3. So the sum simplifies to 3, n plus 3. Our conclusion needs to be that this sum is divisible by 3. An integer is divisible by 3 if it can be written in the form 3 times some other integer. We can factor out a 3 from our expression. This gives us 3 times the quantity n plus 1. Since n is an integer, n plus 1 is also an integer. Let's call it k. So the sum is equal to 3k, where k is an integer. By definition, any number that can be written as 3 times an integer is divisible by 3. Therefore, we have proven our statement. We have successfully proven that the sum of any 3 consecutive integers is divisible by 3 using a direct deductive proof. Let's look at another example of proof by deduction, this time involving geometry. We are given a right-angled triangle with sides A, B, and hypotenuse circa. 3 semicircles are constructed on each side as diameters. We need to prove that the sum of the areas of the 2 smaller semicircles, A and B, equals the area of the largest semicircle, C. This problem combines geometry and algebra. Our strategy will be to find expressions for the areas A, B, and C, and then use the Pythagorean theorem to show they are related. First, let's recall the formula for the area of a semicircle. It's 1/2 times pi times the radius squared. For semicircle A, the diameter is other, so the radius is other plus other 2. Its area is 1/2 pi times other 2 squared, which simplifies to pi a squared over 8. So the area A is pi a squared over 8. Similarly, for semicircle B, the diameter is b, so the radius is b over 2. Its area is pi b squared over 8. The area B is pi b squared over 8. And for semicircle C, the diameter is c, so the radius is c over 2. Its area is pi c squared over 8. The area C is pi c squared over 8. Now we need to prove that A plus B equals C. Let's substitute our expressions. We need to show that pi a squared over 8 plus pi b squared over 8 equals pi c squared over 8. We can factor out pi over 8 from the left side. This gives us pi over 8 times the quantity a squared plus b squared equals pi c squared over 8. Now we can multiply both sides by 8 over pi to simplify. This leaves us with a squared plus b squared equals c squared. This is the Pythagorean theorem, which we know is true for any right-angled triangle. Since our final step is a true statement, and each step was a valid deduction, our proof is complete. We have successfully proven that a plus b equals c by using the area formula for a semicircle and the Pythagorean theorem. Now let's move on to our second major proof technique, proof by equivalence. In proof by deduction, we moved in one direction. If we wanted to prove that 2 statements, A and B, are equivalent, we would have to prove A implies B and B implies A separately. Proof by equivalence offers a more elegant solution. If we can construct an argument where every single step is an equivalence, we prove both directions simultaneously. The structure is A is equivalent to B, B is equivalent to C, and so on until we reach our conclusion Z. This means A is equivalent to Z. This method is particularly useful for solving equations or inequalities, as it ensures that the solution set at each step is identical to the original. To maintain equivalence, we can add or subtract the same term from both sides of an equation, or multiply or divide by a non-zero term. We can also substitute equivalent expressions. However, there are some operations that do not maintain equivalence. Squaring both sides of an equation is a classic example. Consider the equation a equals b. If we square both sides, we get a squared equals b squared. This is not an equivalence, because a squared equals b squared implies that a equals b, or a equals negative b. We have introduced an extraneous solution. To solve an equation like a squared equals b squared while maintaining equivalence, we must use a different method. We can rearrange the equation to a squared minus b squared equals 0. Then, we use the difference of squares factorization to get a minus b times a plus b equals 0. By the null factor law, this is equivalent to a minus b equals 0, or a plus b equals 0, which simplifies to a equals b, or a equals negative b. This is the correct equivalent solution. Let's apply proof by equivalence to a more complex problem. We will find the smallest positive integer, a, for which a quadratic equation has real solutions. Our goal is to find the smallest positive integer, a, such that the equation x squared plus a minus 2x plus a equals 0 has real solutions. A quadratic equation has real solutions if and only if its discriminant is greater than or equal to 0. This is a key equivalence. The discriminant, b squared minus 4ac, must be non-negative. In our equation, a equals 1, b equals a minus 2, and c equals a. Let's substitute these into the discriminant inequality. We get a minus 2 squared minus 4 times 1 times a is greater than or equal to 0. Now we will solve this inequality for a using proof by equivalence. First, we expand the squared term, a minus 2. Squared is a squared minus 4, a plus 4. So the inequality becomes a squared minus 4a plus 4 minus 4a is greater than or equal to 0. Next, we combine the like terms. This simplifies to a squared minus 8. a plus 4 is greater than or equal to 0. To solve this quadratic inequality, we can complete the square. We rewrite a squared minus 8a as a minus 4 squared minus 16. So the inequality is a minus 4 squared minus 16 plus 4 is greater than or equal to 0. Simplifying this gives us a squared term on one side. We get a minus 4 squared is greater than or equal to 12. Now we take the square root of both sides. Remember, this is an equivalence for inequalities. This means that a minus 4 must be greater than or equal to the square root of 12, or a minus 4 must be less than or equal to the negative square root of 12. Finally, we solve for a in both cases. We find that a must be greater than or equal to 4 plus the square root of 12, or a must be less than or equal to 4 minus the square root of 12. The square root of 12 is approximately 3.46. So a must be greater than or equal to about 7.46, or a must be less than or equal to about 0.54. We are looking for the smallest positive integer, a. The integers that satisfy this are 1, 8, 9, and so on. The smallest of these is 1. However, the question asks for the smallest positive integer, a, for which the equation has real solutions. The value a equals 1 gives a discriminant of 1 to 8 plus 4 equals minus 3, which is negative. This means the equation has no real solutions for a equals 1. The smallest integer that satisfies the condition is 8. Let's conclude with a quick look at how to identify incorrect proofs. This is a crucial skill for any mathematician. We will now analyze some common errors in proofs. The most common error is performing a step that is not a valid implication or equivalence. Let's look at an example. Consider this proof. It starts with a equals b and concludes that 2 equals 1. This is clearly false, so there must be an error. Let's examine each step. The first few steps are valid equivalences. The error occurs in the step where we go from a minus b, a plus b equals b, a minus b, to a plus b equals b. This step involves dividing both sides by the term a minus b. However, our initial hypothesis was that a equals b. This means that a minus b is equal to 0. you can never divide by 0. This step is invalid, and it's what leads to the nonsensical conclusion. Since a equals b, a minus b is 0. Division by 0 is undefined. This example highlights the importance of checking the conditions for each mathematical operation you perform. A single invalid step can invalidate an entire proof. Let's recap what we've learned today. We started by defining what a mathematical proof is and why it's essential for establishing the truth of statements. We saw that a proof is a correct argument that moves from hypotheses to a conclusion through a sequence of valid steps. We then introduced logical connectives, which form the language of proof, and emphasized the critical difference between an implication and its converse. We learned about connectives like implication and equivalence, and the importance of distinguishing between a statement and its converse. Finally, we explored two powerful proof techniques: proof by deduction, where we work forward from the hypothesis, and proof by equivalence, where we establish a chain of equivalent statements. We practice proof by deduction, a direct method, and proof by equivalence, which proves both directions of a statement simultaneously. You are now equipped with the foundational knowledge to approach and construct mathematical proofs. The key is to be precise, logical, and to justify every step. To solidify your understanding, here are 5 practice questions in the style of IB assessment. Pause the video and try to solve them on your own before watching the solutions. Here are 5 practice questions. Work through them carefully. Question 1. Prove by deduction that the product of two odd integers is always an odd integer. Question 2. Prove by equivalence that for all real numbers a and b, a squared plus b squared over 2 is greater than or equal to a times b. This is a famous result known as the AMGM inequality for two variables. Question 3. Prove that if p and q are odd integers, then p squared minus q squared is divisible by 8. Question 4. Prove that the sum of any two rational numbers is also a rational number. Question 5. Prove that the product of 3 consecutive integers, increased by the middle integer, is a perfect cube. Let's go through the solutions. First, question 1. We need to prove that the product of two odd integers is odd. By definition, an odd integer can be written in the form 2k plus 1 for some integer k. Let our two odd integers be p and q. So p equals 2k plus 1 and q equals 2 meters plus 1, where k and m are integers. Now, we find their product, p times q. The product is 2k plus 1 times 2 meters plus 1. Expanding this gives us 4 kilometers plus 2k plus 2 meters plus 1. This expands to 4 kilometers plus 2k plus 2 meters plus 1. We can factor out a 2 from the first 3 terms. This gives us 2 times the quantity, 2 kilometers plus k plus m plus 1. Since k and m are integers, the expression in the parentheses, 2 kilometers plus k plus m, is also an integer. Let's call it n. So the product is in the form 2n plus 1, which is the definition of an odd integer. The proof is complete. Now for question 2. We will prove the AMGM inequality for two variables. We need to prove that for all real numbers a and b, a squared plus b squared over 2 is greater than or equal to a times b. We will use proof by equivalence, starting with a known true statement and working backwards to our desired inequality. We know that the square of any real number is non-negative, so a minus b squared is greater than or equal to 0. This is our starting point. Now we expand the left side. This is equivalent to a squared minus 2ab plus b squared is greater than or equal to 0. Next we add 2ab to both sides. This is a valid equivalence. This gives us a squared plus b squared is greater than or equal to 2ab. Finally, we divide both sides by 2. Since 2 is a positive number, this is also a valid equivalence. This leads us directly to the inequality we wanted to prove. A squared plus b squared over 2 is greater than or equal to ab. Since we started with a true statement and used only equivalences, our proof is complete. Let's move on to question 3, which involves divisibility. We need to prove that if p and q are odd integers, then p squared minus q squared is divisible by 8. Again, we start by defining our odd integers. Let p and q be any two odd integers. So p equals 2k plus 1, and q equals 2 meters plus 1 for integers k and m. Now, let's look at the expression p squared minus q squared. We can use the difference of squares factorization. P squared minus q squared equals p minus q times p plus q. Let's find expressions for p minus q and p plus q. P minus q is 2k plus 1 minus 2 meters plus 1, which simplifies to 2k minus 2 meters, or 2 times k minus m. P plus q is 2k plus 1 plus 2 meters plus 1, which simplifies to 2k plus 2 meters plus 2, or 2 times k plus m plus 1. Now, substitute these back into the factored expression for p squared minus q squared. We get 2 times k minus m times 2 times k plus m plus 1, which simplifies to 4 times k minus m times k plus m plus 1. We need to show this is divisible by 8. We already have a factor of 4. We just need to show that the remaining part, k minus m times k plus m plus 1, is an even number. Let's consider the sum of the two terms in the parentheses, k minus m plus k plus m plus 1 equals 2k plus 1, which is always an odd number. If the sum of two integers is odd, one of them must be even and the other must be odd. This is a fundamental property of integers. Therefore, one of the factors, k minus m or k plus m plus 1, must be even. This means their product is also even. Since the product is even, we can write it as 2 times some integer j. So p squared minus q squared equals 4 times 2j, which is 8j. This shows that p squared minus q squared is divisible by 8, completing the proof. Next, question 4, which is a direct application of definitions. We need to prove that the sum of any two rational numbers is also a rational number. We start with the definition of a rational number. A number is rational if it can be written as a fraction p over q, where p and q are integers and q is not 0. Let's take two rational numbers, x and y. By definition, we can write x as p over q and y as r over s, where p, q, r, s are integers, and q and s are not 0. So x equals p over q, and y equals r over s. Now, let's find their sum, x plus y. X plus y equals p over q plus r over s. To add these fractions, we find a common denominator, which is q times s. This gives us ps plus rq over qs. Now, we need to show that this result is also a rational number. This means we need to show that the numerator is an integer and the denominator is a non-zero integer. Since p, q, r, and s are all integers, their products ps and rq are integers. The sum of two integers, ps plus rq, is also an integer. Let's call it p. For the denominator, qs, since q and s are non-zero integers, their product qs is also a non-zero integer. Let's call it q. So the sum x plus y can be written as p over q, where p and q are integers and q is not 0. This is the definition of a rational number. We have shown that the sum is a rational number, completing the proof. Finally, let's tackle question 5, which involves consecutive integers and perfect cubes. We need to prove that the product of three consecutive integers, increased by the middle integer, is a perfect cube. The hint suggests letting the middle number be x. This is a good strategy because it simplifies the algebra. If the middle integer is x, the integer before it is x minus 1, and the integer after it is x plus 1. Now, let's form the expression described in the problem, the product of the three integers, increased by the middle integer. This expression is x minus 1 times x plus 1 plus x. Our goal is to show that this expression simplifies to the cube of some integer. Let's expand the product first. Notice that x minus 1 times x plus 1 is a difference of squares. So x minus 1 times x plus 1 is x squared minus 1. Our expression becomes x squared minus 1 times x plus x. Now we distribute the x. This gives us x cubed minus x plus x. The minus x and plus x terms cancel out. We are left with x cubed. Since x is an integer, x cubed is a perfect cube. We have successfully proven the statement. The expression simplifies to x cubed, which is a perfect cube. The proof is complete. That concludes our exploration of reasoning and proof. You have now seen how to construct rigorous arguments using deduction and equivalence, and how to apply these techniques to solve problems. Remember, the key to mastering proof is practice. Keep working through problems and always ask yourself, is every step justified? Does my argument logically lead from the hypothesis to the conclusion? Thank you for watching.